Okay, so today we're going to continue talking about a larger topic. It's topologies for spaces of mappings between manifolds and sections of vector bundles. Okay. So we had these spaces. I won't go through all of the precise terminology that I won't write down everything I say because I did last time. So remember that if M and N are manifolds, and they can be smooth, real analytic, or holomorphic manifolds, depending on what you want the degree of regularity to be. So the regularity classes, remember, that we're going to consider here are finitely differentiable with a Lipschitz highest derivative, smooth, real analytic, or holomorphic. Okay, so we're wanting to talk about all of these regularity classes, and essentially what we want to do is be able to do this all at once, more or less. Okay, so this is the space of C new mappings from a manifold M to a manifold N, and we also had the C new sections of a vector bundle E over M, and of course the space of just C new functions on M, and so these will be real valued functions unless nu is holomorphic, in which case of course these will be complex valued functions. And so our task here is to topologize all of these spaces. And to do this, we were going to talk about jets, and so I sort of did this all last time, but just to get us back to where we started. So the way intuitively you should think about the k-jet bundle of a manifold M and N is that you have a point, let's say x in M, and a point y in N. And the k-jets at x, y are mappings that map x to y and agree at x. This is a point-wise notion, not a local notion. So they agree at x to order k. So this is basically the space of mappings and their first k derivatives. Okay, and notation-wise, we also had the k-jets of sections of a vector bundle. Okay, so this was a subset, a strict subset of. There's just the bundle of mappings from M to E. And then we had this space whose importance right now may not be completely clear, but we'll see how it comes up in a moment. So T star K, so you can kind of think of this as being like a degree K cotangent bundle at X. So these are the mappings which map X to 0, okay? And so these are the first K derivatives of all such mappings, all right? So we're going to be using these to describe topologies over here. And remember last time I sort of suggested to you that there was kind of a sequence like this without really being explicit about it, and I will not be. Okay, and essentially the way you should interpret this is saying that if you fix a k minus first derivative and consider all the mappings which have that k minus first derivative, and the k derivatives of those mappings, the space of all such things is this tensor product. So this is the degree k symmetric tensor algebra of the cotangent bundle, tensored with the tangent space at y. And the way to interpret what that object is it is a kth order Taylor coefficient. Okay. So this only works for a fixed k, and so what we're aiming for here is we're aiming to get a nice global decomposition of jk into things that look like this, okay? But that's not natural. To do that requires some extra structure. Namely, it requires connections everywhere. Okay, so I'm going to outline how that goes. So the first thing we'll look at is we'll look at the case of vector bundles. Okay, and because we're actually going to use the constructions that we have for vector bundles, and specifically this construction, to induce the thing that we want for k-jets of mappings between manifolds. Okay, so we're going to start with the special case of vector bundles, then we'll specialize that a little bit further to here, and then we'll use that to go back up here. All right, so okay, so if I have a new like this, I have associated with that. I really apologize that my news and my R's look so much the same. If you don't know which one I'm talking about, ask. Okay. So corresponding to a nu, which is the regularity class of the mappings, there will be an R, which is the regularity class of the manifolds, and I will consider smooth real analytic or holomorphic manifolds depending on which of these I'm choosing. Okay, so when I write R, I mean one of these things. Okay, so I have connections. These are just affine connections on M and N. All right, so I won't go through the details of how this works out. There's natural ways to do this. So connections on M and N induce connections on all kinds of things. So you have okay. So you have a connection which I'll denote with a 1 here, okay? And the reason for the 1 will be hopefully clear when the notation when I introduce the additional notation later. Okay. So just by duality, the affine connection on M, which is a connection on the vector bundle consisting of the tangent bundle, just by duality. So essentially, by duality, what I mean is that you take the pairing between sections of this guy and sections of the tangent bundle, and then you ask that the connection act by the Leibniz rule on those. Okay, so that's what I mean by duality. All right. So you get a connection on here. Okay. Then, because you now have a connection on here, you also get connections on all of the tensor powers of that guy. Okay. So I'll call these nabla mk. All right, and again, these sort of backed by Leibniz rule with the tensor product. Okay, so the covariant derivative of a tensor product of things is what you would do if you had the Leibniz rule. Okay, so there's natural ways of doing this. Oh, so sorry, I'm doing vector bundles, so I don't want this right now. What I want is this, sorry. Okay, so I have an affine connection on M, and then a vector bundle connection on E. We'll go to that other case in a second. So this is all still good. Okay. So therefore, you get a connection, nabla K, on. So by restriction to symmetric tensors, this connection. So you have to verify that this that as long as this connection is torsion-free. It'll induce a connection on the symmetric tensors here. Okay, so you get symmetric tensors. So you get a connection on that object over there. Okay, so on S, K, T star M, tensor. Okay, but now we're working with the vector bundle case, so it's tensor E. Okay? So by starting with these two connections, you get a natural connection here. Okay, so how does that help you? Okay, and these are things which you will absolutely never write down in coordinates or anything like that. Okay, so these exist in principle, but if you ever find yourself having to work with these explicitly, think of something else to do. Okay, so what do you have then? So nabla. So if you take a section of E, okay. So I can go nabla E C, okay. So this just means I take, and I have no index here, okay, I really mean this, all right? So this is the covariant differential of the section with respect to the vector bundle connection on E, and what's this going to be? This is going to be, so I'll assume that C here is of class CR, so I can differentiate it as many times as I want without having to fuss with it, okay? So this will be a section of this guy, like that, okay? And then I can do this again, differentiate it again, okay? But now, all right, I'm going to use one of these nabla K guys, all right, when K equals 1. So then I get nabla 1, nabla C. This will now be a section of T2, the degree 2 tensors of the cotangent bundle, like that. Okay, does that make sense? Okay, and then I can keep doing this. So I can go nabla K, nabla 1, nabla, this is E, C, the section of. So this will be TK plus 1, T star M, tensor E, like that. All right. And then I will define P, and I think I go P, K plus 1 is the index I use there. Okay, so PK plus 1 C. What I'm going to do is I'm going to take this guy and I'm going to symmetrize it. Okay, so this will be a section of the symmetric tensor algebra, of course. So this will be a section of this guy. All right. Okay, good. So I've at least produced something which is where I want it to be. All right. So that's good, but you still have a lot of work to do to prove the following fact. Okay. So in these lectures, I'm going to prove very little and possibly nothing. What I might do is wave my hands around a little bit, but I'll at least try to motivate the construction so that when I write results down, you know what they are. Some of these results are elementary, some of them are not elementary, some of them are deep, but none of them will be proved, regardless of which category they fit in. So I'll just state these things as facts, and these are published elsewhere. Okay. So I have a mapping, which I'll write as S, K, E, okay? So this is going to be a mapping from JKE into this direct sum to K Sj M tensor E. Okay. And that goes 0. Okay. So the mapping is this. So I take an element of this jet bundle. Okay. So what's an element of that jet bundle looks like? Well, it looks like a K jet of some section evaluated at some point. Okay. So a typical point in here will look like that. So I take some section, take its K jet, and evaluate it at X. So this means the section and its first K derivatives. All right, all evaluated at X. All right. So this will map to. Okay, so by my conventions here, so I'm going to call this guy notationally. I'll call this now a K with a bar on top. All right. Okay, so the first thing I'm going to get here is just the value of C at X. Okay, that'll be the J equals 0 component of that guy. All right, and the J equals 1 component, of course, is going to be this. Okay, and I do this all the way up to K minus 1 with the numbering that I have. And so it'll be, I'm sorry, I guess I don't need the novel bar right now at least. So this will be P K minus 1 C, like that. Okay? All right, so this mapping is a vector bundle isomorphism. Okay. Moreover, you have a natural commuting diagram which sort of says that this mapping preserves the kind of order structure of derivatives. Okay, so you have these mappings like so. Okay, so this mapping forgets the kth derivative. Okay, we have these guys. This is S, K, E. All right, so the mapping here is just the obvious projection which strips off the kth component of the direct sum. Okay? All right, so for vector bundles, this gives us what we want, right? It gives us a global decomposition of the k-jet bundle in terms of things we understand better. Okay? Now you can always do this locally, and we'll talk a little bit about local things as well, okay? But this allows you to do this globally and gives you very elegant descriptions of these topologies that we're going to be talking about, okay? All right, so this is how this works for vector bundles, okay? Now, just say a few words about the proof of this. If you sit and you look at this for a second, you can imagine it's going to be a proof by induction. And you can imagine doing this explicitly in coordinates. And maybe you can even do that. But it turns out that there's a very elegant way to kind of do this by writing down some commuting diagrams, including the one I just erased here about the sequence of jet bundles. And do this by doing some diagram chasing. It's a much more elegant way to do it. It's not fast, but it prevents you from having to think about what these coordinate calculations for these guys look like, because it's quite disgusting what that thing is going to look like for a large K, right? but you don't have to know that. All right, so you have this isomorphism. Maybe you're never going to write it down, but you have it, and we fix it. So this isomorphism certainly depends on the connections that we've chosen. Okay, but what we'll see is that the topology, we're going to define the topology using these guys. The topology does not depend on those choices of connections. Okay, all right. So, so this is for an arbitrary vector bundle. Okay, now let's specialize this to functions. And so a function, okay, and so you can think about, so f might be r or c, okay? And derivatives could be complex derivatives. There's nothing stopping you from doing that, okay? And so a function is just going to be a section of this trivial bundle, okay? So the idea is that a section is going to map x to x f of x, the value of the function at that point, okay? All right, so that's a vector bundle, and all of this stuff specializes, and so you get, this is just notation at this point, a mapping like this. And so actually we're interested in looking at the sections which evaluate to 0. And so you'll notice here that this isomorphism will, because of this commuting diagram, will preserve evaluation to 0. Okay, so in other words, this whole business restricts to a connection on, or to a decomposition of this thing. So it's going to be, okay, now the sum goes really from 1 because everything is evaluating to 0, so you get nothing at degree 0 in that decomposition there. Okay. Right, so you just get that, okay? Because E is the trivial bundle, so you're going to be tensoring with R, so or F, and so you just end up with that thing back again. Okay, so you have an isomorphism like that. Does that make sense? Okay, so now we're going to use this construction somehow to talk about decompositions of jet bundles of mappings between manifolds. All right, so what you want to look at is you want to think about jets of mappings like this in the right way. So I'll say this maybe as a fact. Okay, so there's a few facts here. So the first one is going to be that this thing has the structure of an algebra over F, and it has the obvious. It's a vector space, obviously. Even before I make this decomposition, by the way, it's a vector space. It's a vector space just because it's the sections of a vector bundle. Okay. But it also has a product structure, and so the product structure is like this. So I take two elements of this, and what do elements of this look like? So remember, these are k-jets of functions that evaluate to 0. So two of these guys, well, one of these guys is going to be the k-jet of a function evaluated at a point. Okay. So what I want to do is take the product of that with another one of those guys, so the k-jet of another function g, and there's only one possible way to do this. And you just take the jet of the product. So the product of the jets is the jet of the product. And then the thing you have to verify to make sense of that is that that's well defined. Okay. that it satisfies the properties of an algebra just follow from the fact that that thing is an algebra. All right, so it's the well-definedness of that thing that you need to check. Okay, so you can do that. Okay, so given that, okay, then all right, so we're going to look at k-jets of mappings from M to N. Okay, so it's going to be a bijection from one of these jet spaces at x and y. So these are jets of mappings from x to y. Okay, so there's a natural bijection from here to the space of F algebra homomorphisms from, okay, those F algebras, okay? And it goes backwards, right? So it goes from T star K Y N to T star K X M. And what is that, or what satisfies that, that mapping? Or what does that mapping satisfy? So this is defined by, okay. So let me call this bijection, I probably have a name for it and I am totally not remembering it now. So for the purposes of this moment right now, let me call this iota K M N. Okay? So, iota K, K, M, N, okay? So that's going to take a k-jet of a mapping from N to N. So this is going to take J, K, phi of X, okay? So phi is a mapping, smooth or whatever you need it to be, from M to N, which maps X to Y. Okay, and I take its k-jet and evaluate it at X. So that's going to be an element of here, and then I apply this bijection to it. Okay, so I'm telling you that this bijection is going to take an element of this to an element of this. Okay, so this thing right here, okay, wants as argument something from here. So something from here is going to look like this. Okay. And again, there's only one possible thing that this can be, and it is J, K of the pullback of G evaluated at X. Okay. All right. So if you think about what's happening here, so this is just composition, right? So pullback is, this is just G composed with phi. And so when you take k-jets of that, the k-jets, when you write that down sort of explicitly in coordinates or something, are going to be computed using some disgusting chain rule, high order chain rule calculation, okay? But what it does, and it's really, really not completely clear, that this map is a bijection. That's kind of the hard part here. That you get a bijection from the space of k-jets to the space of algebra homomorphisms from this guy to these guys. Okay, so that's actually not that hard to prove, but that's the thing that you have to prove there. All right. Okay, so the point is, and so let me. Okay, so if I have F algebras A and B, let me write HOM as algebra homomorphisms. If I want to talk about vector space homomorphisms, I'll make the convention that I'll put the symbol, whatever the field is down there. Okay, so when I write HOM with no subscript here, that means I forgot it, or it's an algebra, a set of algebra homomorphisms. Okay, so this is algebra homomorphisms from A to B. Okay? All right, so this gives me a bijection from this space to this space. Okay? And so you can see now how I might use this decomposition, right? Because what this decomposition does is it decomposes the arguments of the Hom here. Okay, so this is decomposed into a direct sum. This is decomposed into a direct sum. You have the commuting of that diagram that I just erased. Okay, and that's enough to give you what you need. Okay? So the fact here, so now we do what I started doing over there. Connections. T nabla M and nabla N on M and N. Okay? All right, so that gives me, for both M and N, this guy, right? Okay. Okay, so let me see if I can write this down. You could write it down right now, okay? It's one of those things where once you've assembled all of this data, there's only one thing that can possibly happen here. That doesn't mean that it's easy to prove, but sort of by naturality, you could at least write the statement, okay? So there exists a bijection. Okay, so I'm going to call this one SK MN. All right, so this bijection is from jet bundles of order K like this into these guys. Okay. All right. So actually, sorry. Before I do this, so I'll maybe do it here. Okay. I want to keep that up there for a second. All right. Yeah, sorry.
Is the associativity there easy to see?
Associativity? Because it is for functions. It follows from the Leibniz rule. I don't know how hard it is. Like in coordinates, right? Or even yeah, exactly. So yeah, you're right. It's possibly not obvious, but certainly it's true. Yeah. Yeah. A lot of these things they seem obvious, right? They're natural statements that you want to make, but some of them aren't so easy to prove. And possibly that's one. I don't remember. I did this years and years ago. Okay, so actually what I need to think about are Homs of these things a little bit, okay? Let's look at Hom of T star K, Y, N. Actually, let me do this. Let's look at, that's the best way to do this. Okay, so these are really, these are going to be spaces of derivatives. Okay, so let's look at the simple case. Let's look at U and V be, let's stick to the real case just so I don't say anything wrong inadvertently. So these are going to be real vector spaces. Okay, and let's imagine we have map, and we're going to be doing calculus now, right? So these are going to be finite dimensional. Okay, and we're going to basically do these kinds of jet constructions kind of by hand here, using normal derivatives. Okay, so what we want to think about is we want to think about k-jets of mappings. So I really want to motivate what this result here is going to be. Not prove it, but motivate it. From U to V. Okay, so U you should think of as being M, and V you should think of as being N. Okay. Okay, so these are going to be ordered kind of by derivative. Okay, so you're going to get so if you have a mapping, let's say phi from U to V. Okay, the jets of this guy are going to be very simple. So okay, so it's represented by J, K, phi of evaluated at some point. Let me call it U. Okay, so you can just write this as phi of U, and now we can just take normal derivatives, right? And these come with a natural decomposition. Okay. All right, so the point is, if you're going to be studying k-jets of mappings like this, you're only going to be taking the first k derivatives. Okay. So really, therefore, you can restrict yourself to taking k-jets of polynomial functions, okay? Because when you take, you're only going to see the first k derivatives, so you're only going to see the first k terms in the polynomials here. And so maybe what I really mean here is the value getting at 0, okay? Jets you always evaluate at a point, okay? So we'll evaluate at 0, and then all the higher order derivatives will disappear. Okay, so the point is, we can think only about polynomial mappings from U to V if we're thinking about jets. Okay, so what's a polynomial mapping from U to V? Okay, so it'll be polynomial of degree k, right? So what's that? Okay, so these are elements of. Okay, so what's a polynomial function on U taking values in V? Well, it's simply sk of U star tensor V. Okay. So for the purposes of taking jets, locally you can kind of think about just polynomial functions. All right. So now let's think of these jets as being not jets, okay, but using the fact that I just erased as being algebra homomorphisms, okay, because we know there's a correspondence between jets and algebra homomorphisms, okay. By what I just erased, this space is really hom, okay, algebra homomorphisms from U star, okay. Hold on, let me make sure I get this right. So it's going to be right from so direct sum, okay, j equals 1 to k, all right, of, so it'll be sj u star, okay, into direct sum j equals 1 to k sk v star. Right, does that make sense? Right, by the fact that I just erased, the space of k-jets are the algebra homomorphisms from t star k y n, and so I got my u and my v backwards. It should be v, and this should be u, so that should be u v, okay? So from t star k y n, so that is, by this decomposition, that space. You see what I'm doing?
I'm just wondering why you don't have a direct sum over some index off the left-hand side.
Oh, good question. I do. Thanks. Yes, that's right. I mean, yeah, okay. Yeah, thank you. So if now I'm going to restrict myself to things that map 0 to 0, and then that'll be just from 1. Okay, yeah, thanks. Okay, good. All right. Okay, so this space is T star K Y N, and then we know that this space is a set of algebra homomorphisms from here into T star K X M. Okay, so that's kind of the local version of that. And I've kind of written it in a way that you can imagine this in coordinates is the point. Okay, so now, okay, so where's this thing going to go from and to? Okay, so we know by what I just erased over here that this is going to go, each element here is an algebra homomorphism. Okay, and by this statement here, algebra homomorphisms are these guys. Okay, does it make sense? So what I get is this. S, J, T, star M, tensor, Tn. Yes. Okay? Does that kind of make sense? All right? And so there's two steps here. One is you identify this with algebra homomorphisms of these kinds of spaces. And then the other step is that you think about what algebra homomorphisms look like. Okay? And they look like this. Okay. All right. And so you have the natural commuting diagram. Okay? And I'll draw it quickly. So J, K, M, N. All right. Okay, so that diagram commutes, and okay, and you have to kind of use the interaction of this mapping, okay, with this mapping. Okay, so how does that interact with that mapping? All right, so I'm going to take SK and apply it to some mapping, or to the kjet of some mapping. All right. Okay, so that takes values in here. All right, but so I'm going to use this isomorphism, okay, implicitly. Okay, so I will think of elements of here as being algebra homomorphisms between these two guys. All right. So therefore, okay, so I'm assuming here that phi is a mapping that maps x to y. So g is going to be a function which evaluates to 0 at y. Okay.
Oh, sorry, so I see. But you have basically the mapping going from jk of n, right there. There's no restriction there on the left.
Well, so jk of mn will map functions that take values at 0 at x. They'll also have the value 0 at y because it's composition, right? The bijection with algebra homomorphisms is composition. Yeah, so 0 evaluation is preserved. Yeah. Okay. And when I wrote down the bijection that I erased, I really was using spaces of functions that evaluate to 0 when I wrote that bijection. Yeah, and so the question should have been asked then. Your question, yeah, that was the right place to ask that question, yeah. Yeah, but you know what I'm saying. Yeah. Okay? Okay? So this, oh, sorry, I didn't mean that. Because I want to use, because I'm going to do this, right? And so JKG does not live there, but N of G lives there. So what I really meant to write was this. Like that, okay? And, all right, does it make sense? All right, because this now lives, this is a mapping from this one into this one. So I have to apply that mapping to the SK version of JKG. And of course, then it has the obvious property. Like that, okay? And that one should go like that. All right? All right, so you have these nice bijections between jet bundles, which preserve these algebra structures on spaces of mappings. Okay? So in other words, this bijection does what you want it to do. It gives you a decomposition like this, okay? But it preserves all of the structure that this guy has, okay? And it just adds some additional structure. But it doesn't kill any of the existing structure, right? So it does exactly what you want. Okay, so let me summarize. So we have bijections or isomorphisms. So let me just say structure preserving bijections like this. Okay, for the vector bundle case, we have that. In this case of kth order tangent vectors, we have this. Okay. And then for jets of mappings between manifolds, we have this. To K, right? So I should be careful to understand what this is. This is a vector bundle over M, okay? This is a vector bundle over N, okay? This is a vector bundle over the product, so this tensor product. So what you do, of course, is you take this one, you pull it back to the product, M cross N. This one, you pull it back to the product, M cross N, and that's the tensor product of those vector bundles.
You usually see those by a square.
Yeah,
Box, crossing side.
Oh, is that the product? Oh, okay, I've never seen that notation before. Okay.
That's right.
Yeah, that's what they do that. I didn't know the reason.
Okay. Too hard to draw.
I know.
Okay? All right, so that's what we've done, right? And all of these things, so let me just make sure I summarize what they depend upon. Okay? So this depends upon nabla M, a connection on M. M, and a connection on E. This only depends on a connection on M, and this depends on a connection on M and a connection on N. Okay? So the way to think about this intuitively is that locally, just like this formula that I wrote down over here, locally, if you're talking about mappings between Euclidean spaces, you can naturally decompose the derivatives order by order. Okay? You cannot do that globally, naturally, okay? But this gives you a way, non-canonical, okay? So it depends on all of those objects, but it gives you a way of decomposing derivatives, which is what jets are, order by order. Okay? All right. So now what? So now there's some very easy stuff to do just for a second. Okay, so I want to put metrics on let me actually for the purposes now, I want to put metrics on these things. Like that. Okay? And I mean just normal, plain old distance functions, okay? All right. Okay. Okay. And so when I say this GE is a vector bundle metric, or a fiber metric. Okay, so at each point it gives you an inner product on the fiber of E at that point. Okay, so I need that structure. Right. Okay, so we'll look first at the vector bundle case. Okay, and then because the vector bundle case looks like that, and then that'll kind of tell us what to do in the case of jets of mappings. Okay. All right. So first, let's look at J, K, E. Okay. All right, so what do I have? I have a connection. I still have all of those connections. Okay, those choices have been made and I fixed them for eternity. And I will now make these choices and fix them for eternity. All right. Okay, so what do we have now? So we have, for a point E in E, what does a connection do? Well, one has multiple interpretations of what a connection means. Over here, with all of these constructions, I'm using the differential operator properties of connections, okay? Because I'm differentiating sections and associating those with jets, so that's all about differentiation, okay? Now, I'm going to use a different interpretation of what a connection is, and that is that it gives you a decomposition of tangent spaces, okay? So it's going to give us a decomposition of the tangent space to E at this point E. Like that. Okay. All right, so it gives me a way of decomposing my tangent space at E into a horizontal and vertical. Okay. So there's a picture you should have in mind here. So here's M, here's E. Okay, so at a point here. Okay. Now there's just, you can see it floating off in space there, right? There's no way, there's a natural vertical component to this thing, so it's just the tangent vectors tangent to the fiber. That'll be the vertical component, so this one is isomorphic to E sub x. But you'll have many choices possibly of a complement to that, okay? Any one choice is defined by a connection, okay? And it's not so, I mean, it's important here, but it's not the point. But let me just say that the fact that nodla E is a vector bundle connection means that the mapping from here into the vertical component, the projection, is linear. No, I don't mean that. What I mean, sorry, is that this mapping from here into here is linear in E, sorry. Okay? All right. Okay, so Okay, so now what I will do is I'll use this decomposition to give me a Riemannian metric on E, okay, and therefore, and this actually now works for any vector bundle, okay, and so it gives me a Riemannian metric on these guys just by sort of taking the special case when E is equal to JKE. Okay, all right, so then we define a Riemannian metric on E by, okay, I'll put a bar on top of it. Okay, so this will be just an inner product on the tangent spaces of E. So I'm going to take two tangent vectors. Let's say U, E, V, E. Okay, so these are tangent vectors to E at the point little e. Okay, right? So the projection here I'll write as U maps to horizontal part of U and vertical part of U. For the purposes of notation, okay, so this projection, this is the horizontal part of U, this is the vertical part of U. Okay, so there's an obvious way to do this. Okay, so what this does is it gives you an inner product on each of these subspaces, okay, a horizontal and vertical subspace induced by GE and GM, and then declares that that those subspaces be orthogonal. Right. Okay, all right. So that gives us a Riemannian metric on E. Okay, now, given two vector bundles, E and F, let's say, over M. Okay, so now what we're going to do is we're going to take this construction and we're going to kind of just bootstrap it to give us a connection on here using those decompositions. Okay, so given two vector bundles E and F over M, we have with fiber metrics G, E, G, F, we have a fiber metric on the tensor product. Okay, and it's defined by it has more or less obvious definition. Okay, so all right, so I define how it acts on elements of the tensor product that look like this, and then you extend it by universality of the tensor product to the whole tensor product. Okay, so it's going to be the obvious thing. Okay, so you can verify that this gives you something well defined, and that it's an inner product on the whole tensor product. Okay, that's a homework problem in algebra. Okay, so therefore, okay, all of this data, and let me just sort of re-encapsulate it here. Okay, so my construction depends on all of that stuff. So it gives fiber metrics on these vector bundles. Right? Okay, so we have fiber. So first of all, let me just make sure we understand what happens here. Okay, so GM gives me inner products on TM, and by duality, therefore, inner products on T star M. And then by tensor producting, okay, and restricting to symmetric tensors, I get inner products here.
Sorry,
Yeah.
shouldn't we have the product of those two EGF there? That's supposed to be our sum.
Oh, yes, you're right, thank you.
Because
Yes,
it's
yes.
tensor-
That's right, thanks, yeah. Yeah, thank you. Yeah, that's right. Okay, so this construction gives you inner products on the symmetric tensor algebra, and then again gives you an inner product on here. Okay, and then by just taking direct sums, you get an inner product on there. Okay, so we have fiber metrics on here now. Okay, all right. So so let's say we have a fiber metric G K. All right. Actually, this one I want to write as G bar K. GK I use for the for each of these individual components, but on here I'm going to use G bar K. Actually, I don't even want to do that. Let's say that's that. G bar is going to be my final thing. Let's call this one GK. Okay. Then I apply this construction again. You understand what I'm doing here? So I'm starting with a general E, and then I'm sort of applying that general construction to this case, and then I go back to the general construction here, but with E now replaced with JKE, and so what I get is I get a Riemannian metric on JKE. And this one I call G bar K. Okay, does that make sense? So there's normal, good old metrics on E. Okay? And now you can see that in a similar manner, okay, so we get a Riemannian metric, and this one I'll call G bar K, M, and N. And so maybe I should really call this one G bar E. These are transitional constructions. We're not going to be referring to this notation too awfully much. Okay, so we get a Riemannian metric on J, K, M, N. Okay? All right, just because JKMN has a correspondence with some tensor product, or sums of tensor products. Okay, so this induces, and again, these metrics these metrics have some properties. Okay, so because this metric comes in this very, so say for E, comes in this very specific way, there's some things about the corresponding distance function. Okay, so Riemannian metrics always will give rise to normal distance function metrics on the manifold. And the distance function has some properties, okay, that we're going to kind of hurdle over, but they're useful. But the point is, you are never going to calculate this, right? So I'm not standing here saying that you're going to be writing these distance functions down in examples and calculating with them. They are incalculable, okay? And why are they incalculable? How do you compute the distance function in with respect to a Riemannian metric? You have to find geodesics and solve differential equations. Right? So that's in the category of things you can never do. Yeah.
So you have already a Riemann metric on E,
Yeah.
and you
A fiber metric.
I see.
Yeah. Now it's on the whole space, on the manifold
space,
E.
On the total space.
That's
I see,
right,
the
yeah.
total, basically.
That's right, yeah. We're not going to be so interested in it on E, okay, but we're definitely going to be interested in it here. Yeah. Okay, and you know, so when you're thinking about this thing here, you know, this is really going to be most applicable here for E itself and JKE. Mostly, I'll just be using the fiber metric. Yeah. Okay, good. All right, so we now have a distance function. And I'll write this as d bar k on m cross n. That is incalculable. I want to make sure that we understand. I'm not proposing that this is practical, but you never really compute using distance functions anyway. You just use the distance function. Okay? All right. So, what time do we have? 10:08. Okay, so now what we're going to do is we're going to define topologies on various spaces of mappings using these distance functions, okay? So in the short time that I have left, we'll do this in kind of the easiest case, which is the case of mappings of class CK. Okay, so I first will look at the most general case here. We're going to have multiple descriptions of these topologies, okay? And the multiple descriptions, for example, you know, there's some work you have to do to show that these multiple descriptions are equivalent, and one of the consequences of that is the descriptions of these topologies that I will use most often will be using these constructions here. And it's not a priori obvious that these constructions are independent of all this data that I've chosen, because there's a pile of data that goes into defining just that guy, right? But I'm going to be defining a topology, and because I have these equivalent descriptions, some of which do not depend on those guys, that will prove that once you actually show their equivalent, which we're not going to do, but I've done, that will prove that the topologies defined using all this business are actually independent of the choices that we made. Okay? All right. So let me give you the basic description here. So first, we'll start by thinking about the compact open topology. And I kind of don't remember, this is a kind of general construction that you can make for topological spaces, for arbitrary topological spaces, and then when your topological spaces have certain properties, it boils down to something simple to understand. I forget exactly what those properties are, so I'm just going to assume that we're working with manifolds. So let's start with C0. Okay, and our manifolds will be Hausdorff and second countable, so everything I say will be true. Okay, so the compact open topology for C0 of n is the topology whose converging sequences those converging uniformly on compact sets. Okay, so on every fixed compact set, when you take a sequence in here, if it converges uniformly, and uniform makes sense now because these guys are metric spaces, okay, by choosing just the metric on M and N corresponding to GM and GN. Okay, so we have metric spaces. Right, and so there's an assumption that I'm making here, or something I'm assuming that the space is first countable, so it's actually defined by its converging sequences, and it is. Okay. All right, so that's a simple way to understand the compact open topology for continuous functions, continuous mappings between manifolds. So we're going to use that to think about what the topology is for spaces of finitely differentiable mappings. Okay. The CK compact open topology for CK MN, okay, is the topology for which the mapping, okay, so I'm going to have a mapping from CK MN into the set of continuous mappings from M into JK and N. Okay. So this mapping I'm going to call JK. All right, so it's going to take some mapping like this, and it's going to map it to simply JKP. Right? So it's the mapping that assigns to, and so phi has to be at least of class CK, of course. So I can take its K jet, and the assignation of phi of its K jet to phi, that defines this mapping JK. Okay, and I declare this mapping is a homeomorphism onto its image. Okay, because this now has the compact open topology that I defined over here, because JK is now a metric space, I just put a metric on it. Okay, and this is very simple to describe. A sequence in CK and converging so a sequence like this, converging to phi is one that converges along with its first K derivatives. And compact subsets of M. Yes, thank you. Yeah. Okay, and that more or less follows just immediately from the definition. Okay? All right, so we're getting started here. Next time what we'll do is we'll talk about the C infinity compact open topology. We'll talk about the holomorphic topology, and then we'll talk about the real analytic topology. That last one takes some time. Okay, so that's next week.